Recording in progress.
Now, we discussed yesterday the rotational partition function. And as you recall, the context was that we approximated our total energy. So this is an approximation, right? Strictly speaking. We cannot do that. But if you do that, we can separate out the partition functions. And in particular, we consider the three degrees of freedom in terms of translation, rotation, and vibration. Now, translation then is this first part, which we discussed last week using the Schrödinger equation for the particle in the box. And yesterday we talked about this middle factor, which is resulting from the Schrödinger equation of the rigid rotor. I would love to continue that today, hopefully conclude things, and then get started with this third factor here, which stands for the vibrational partition function. So we are in chapter 4.3 on the rotational partition function. And in particular, we talked about this diatomic here, drawn here. So two atoms that are bonded at a rigid distance r, small r, with a reduced mass mu. Okay. Now this mass mu enters your moment of inertia I, which then enters the rotational constant, such as it is shown here, the constant B, which is often then reported in spectroscopical studies or the literature. So given that rotational constant and given the molecular species, you know the bonds, the chemical elements, that is their mass, and this is then allows you to determine the diatomic distance, for instance. We then introduce this characteristic temperature, capital tau r, which is really helpful because we can rewrite our energy in terms of tau r. And in particular, our partition function then, together with the beta term, has in the exponential Boltzmann factor just the quantum numbers here for your rotations and this ratio between the characteristic temperature and the real temperature. Now, we found out that this sum can be approximated by this integral in the continuum approximation. And what we end up with is that our rotational partition function is approximately T over this characteristic temperature, T over tau r, okay? And again, if we prefer to express things in terms of moments of inertia, we can also write it like this, and the temperature is hidden in the beta here, right? So Q equals T over tau r, and we then went ahead and discussed some limitations. So for larger values of your Q, right? So again, this is your Q rod. When these values are larger, then the error becomes small. And if your Q is very small, then the error is becoming larger percentage-wise. So this is reassuring news, right? Since we write the total partition function as a product of the other partition functions, if a degree of freedom does not matter, then that partition function would be close to 1. And in that case, when it doesn't matter, then we collect a little error here. But when that partition function matters a lot, then the error is small. So we then looked at some specific examples of a whole bunch of diatomic molecules. And we then wrote this, the Q rod at 300 Kelvin in this separate column here. So this Q rod is T over tau R. Now, if you actually enter these values, and I'm just noticing there's an error here. This is not tau R over T, but tau R in units of Kelvin. Okay. So it carries temperature units. And so this is it can be measured in Kelvin, while Q is dimensionless. So what you will notice if you divide 300, so this is at T equals 300. If you divide it by tau, you don't necessarily get the values in the Q rod column. And the reason for that is that what's actually reported here is not T by tau R, but T by tau R times sigma. Okay, and that is an extension of our partition function that is due to what is known as the symmetry factor. Sigma. Now, this symmetry factor comes about due to the following consideration. So QR corresponding, roughly speaking, to T over tau R is valid for all hetero diatomics. Okay. Now, if you consider a heterodiatomic, you can track the atom for its full rotation, right? If by contrast you consider a homodiatomic, the atoms are indistinguishable after 180 degrees rotation. Sorry. Indistinguishable. And so we need to scale the whole thing down by a factor of 2 in order to avoid overcounting the number of states. Okay, and so we more generally use Q rod equals T over tau R times sigma. Okay. So the sigma is the symmetry factor. And for a homodiatomic, sigma equals 2. For a hetero, diatomic, sigma equals 1. This, in fact, is also can be extended to nonlinear systems. Right? This is something in this discussion we right now we haven't talked about this yet, because we are discussing these degrees of freedom for this system, the diatomic. This is the example we are still working on, right? So this is a little bit of an excursion to now bring up molecules with more than 2 atoms. But you should note this, that in general, the sigma is more general. So this also enables extension to nonlinear molecules. And the symmetry factor, you will find it also listed in the spectroscopic tables of molecules. For example, if you consider the planar molecule H2O, you know from symmetry there's a C2 axis, and this implies that your sigma would also be equals 2, since you cannot distinguish anymore the atoms after such a rotation. Similarly, for ammonia, you would have a C3 axis for a rotation around this axis, leading to a symmetry factor of 3. Now, as you add more atoms, this can become more complicated. But basically, what we find is that, for instance, the symmetry factor for methane will correspond to 12, right? So the more possibilities there are to get through a simple rotational symmetry element to get to the same configuration, the larger your sigma. Now, if we go back to our little table here, we can now note the corresponding sigma factors, and let me enter the sigmas next to these molecules. So for H2, it's homodiatomic. We would have a symmetry factor of 2, right? So your 300 Kelvin here divided by 2 gives you 150 divided by 90, and then is roughly this 1.7, right? So now the numbers should make more sense. The sigma for HCl is 1, right? The sigma for HI is 1. Here you simply see the impact of increasing the mass, right, from Cl to iodine, and increasing the bond length. You see the growth in your rotational partition function by nearly 1/3. Now, interestingly, N2 again is a diatomic, right? So we have a sigma of 2, while CO is a diatomic, a heterodiatomic with 1. Now, the bond distance and the effective mass of these two molecules are very similar. And now you see this is the nice example for distinguishing these two molecules. You see that due to the symmetry factor, the partition function of CO is twice as large as the one of N2. Right? So the contribution to the internal energy because of symmetry from the rotational part, right, is twice as large for CO than as for N2. Okay. Now the other molecules also have symmetry factors, right? For CO2, this is also like homodiatomic, right? You cannot distinguish after 180 degrees, even though it already has 3 atoms, but it's still a linear 3 atomic molecule. And then methane has a surprisingly low partition function, but there is a symmetry factor of 12, right? And so that means this is damped tremendously because of its high symmetry. Okay, are there any questions, further questions on this? Doesn't seem to be the case. I also do not see questions in the chat. So let's continue then. Using our expression for Q rod. We can easily calculate once more the contribution to the internal energy, as we have done already above, but we can see how we can recover this. So for that, as you recall, our averaged energy is kBt square, and now d logarithm q with respect to t, right? That's the rotational contribution to the internal energy. Now, since q rod is simply t divided by something, we can separate that out in the logarithm, right? So then this becomes dt logarithm t plus t independent terms. Right. Now, that is, of course, nothing else than 1 over t, and hence you see that your rotational part must be n kbt, and again this corresponds then to an internal molar energy of RT. Okay. There's one more interesting remark I would like to make, or I'd like to make a remark about an interesting fact, which is that commonly we assume that when we solve Schrödinger's equation, that the lowest level is populated most. Okay. And this is, of course, dependent on the temperature, right? And there's a Boltzmann distribution. And in particular, the rotational distribution is known counterintuitively to have the maximum of the occupation to be not in the ground state. Okay, so in particular, if we now consider the distribution of rotational states J, then we can write down the Boltzmann probability would correspond to 2J plus 1 times e to the minus j times j plus 1 tau rod over t. Okay, and this whole thing divided by q rod. Okay, now we can insert our q rod, our expression here, and we find 2j plus 1 times tau rod divided by t e to the minus j plus 1 tau rod over t. And so you can find the p as a function of j. So with increasing j, our energy goes up. We ask this question now, at which j is pj maximal. Okay. And the answer would be that we have to set the derivative of pj to 0 and then solve for j. Okay. And we can do that pretending that j is a continuous function. You can find a j and then you could jump to the next integer j. But what you should find then is a function which looks something like this, where typically, oh yeah, this is pretty, I didn't pay attention. So it's roughly something like this, where your maximum at room temperature is between 5 and 10. So this is these are the most occupied, the most likely states. Okay. And I believe in one of the tutorials you also encounter this question. Okay, are there any questions at this point? That doesn't seem to be the case. And then I'd like to move on to subchapter 4.4, where we will discuss the vibrational partition function. Again, starting out first with the diatomic. Okay, so our first subchapter A will be a diatomic. And now we completely ignore all rotation. Okay, so in the rotation, we ignore translation and vibration. Now in the vibration, we ignore all rotation and we focus on the internal degree of freedom that is being sampled here. And so for this diatomic, we like to make the harmonic oscillator approximation, right? Again, similarly to the particle in the box Schrödinger equation, you hopefully have also encountered already the harmonic oscillator Schrödinger equation, right? And this is the Schrödinger equation for the internal vibration that's happening. That is, we consider a simple harmonic oscillator. Now, the harmonic oscillator is so pervasive in theoretical physics that people like to give it an acronym, HO, and we can use it to solve the Schrödinger equation, and then we also call it the quantum harmonic oscillator. Okay, QHO. The picture is simple. Again, we have a diatomic with two atoms with a certain mass. And between these two atoms is a harmonic spring. And this is also known as Hooke's law. that you say that the force as a function of the distance should be proportional to the distance. Now, since the force is the derivative with respect of the energy with respect to x, this means that the energy of x must be proportional to x squared. Okay. And so Hooke discovered this law for springs, harmonic springs, and so this is where the quadratic potential comes from in your Hamiltonian, in addition to the kinetic energy for these atoms with their mass moving. This will form your Hamiltonian of the harmonic oscillator, and you will get a wave function. And this wave function now is not for rotations. This is a wave function for vibrations. Okay, so your atoms and their movement, right, is being accounted for by this nuclear wave function, and this will exist again for a spectrum of discrete solutions, your vibrational energies, energy eigenvalues, and again, it's a Schrödinger equation. So we have an eigenvalue, the form of an eigenvalue, right? So this is the vibrational Schrödinger equation using the Hamiltonian of the harmonic oscillator. Okay. Now, again, I hope you encountered this already in your quantum course. So we do not have to solve this ourselves, even though it's a beautiful chapter in introductory quantum mechanics. And we note directly the solution. We only typically, when we say solution of a Schrödinger equation, we are referring to the eigenvalues and the states, right? So the wave functions, that's also part of the solution. But for the partition function, only the states matter. So we focus only on the energy states. And so these states have eigenvalues which grow linearly in the quantum number. So this means that as I increase my quantum number, my eigenvalue goes up in equidistant increments. And this is what you see here. Now, if I look again at the energy profile as we have seen it, and I believe it's already 2 weeks ago, I shared a slide of a picture with such energy profiles for the H2 molecule. And this is the energy. Then these were different electronic states. And this is the ground state. And here you have the first excited state. And then in each electronic state, we have vibrational levels. So these are epsilon vib 0 epsilon 1 vib. And this is for the electronic ground state. So I should add here the electronic state as a second index. And then I have my vib, my ground state in the first excited state. And my second state, my first excited vibrational state in the first excited electronic state, and so on and so forth, right? And just as a reminder, within these levels, we have the rotational levels, right? Okay. So what we do now, when assuming that your potential is a quadratic function, what we do is that we say our, and this is the interatomic distance, R, our potential here, our electronic ground state, or really any other state, but it should be a binding state. We approximate this by a quadratic function, right? So this would be our harmonic oscillator potential, which is proportional to simply x squared. Sorry, r squared, right? And it's in this potential that our eigenvalues are exactly equidistant. Now, this becomes particularly problematic as you start populating vibrational states that are higher up, right? So if you start heating your system, then the harmonic oscillator is a poor approximation. And what you should really see are eigenvalues that are much lower because they have to fill a much wider potential, right? Now, this shift from the harmonic to the more realistic, downwards to the more realistic vibrational level, this shift is also known as anharmonicity. Okay. This is a little bit funny because in reality, right, the harmonic oscillator is the funny approximation, not reality. But we presume that that model is a good model, and then when it breaks down, we call it the anharmonicity, right? And this anharmonicity lowers our eigenvalue. So if I look at my vibrational eigenvalue, I can now correct it with a constant, which I call anharmonicity constant. And this is also for level n plus 1/2. And it's actually quadratically it grows quadratically, this correction, with the eigenvalue, okay? Now, for typical thermal excitations, we can neglect this anharmonicity. So would be for very high temperatures, right? So for ambient usual thermal fluctuations we like to neglect the anharmonicity. Okay, so we are really left with the pure harmonic solution, right, of the harmonic oscillator at n being n plus 1/2 h times nu. And this nu is the frequency, and it's related to the strength of the spring, right? So to which extent the spring will reattract the two atoms when you stretch them. This is a very important measure, and you have to be very careful, because in common jargon we call this also the bond strength, but it's really the curvature, right, of this potential. So it does not tell you how deep the potential is. I can have a bond length, a bond that's very weak, that has not a deep well, but a very stiff potential with a high curvature. And so this would have a high frequency, and we would also call that the bond strength. So one has to be very careful and consider in the context what is being implied when such statements are made. Now, this frequency is 1/2 pi times the force constant over the reduced mass and the square root. So this is this vibrational frequency. Now, before we enter considering the partition function, we make one more change that helps a lot later on with the equations. And this is the following, and this is now subchapter B, because everything in A was sort of things, just a recap of what you should know already from your from previous quantum lectures. So now we do something specific for our partition function, which is that we make a simplifying assumption of shifting the spectrum towards the 0 point. Okay. So you may recall that the solution of Schrödinger's equation for the harmonic oscillator gives you, even for the lowest state, an energy contribution, which is known as the 0 point vibrational energy, right? And you can consider this by using the quantum number 0. You will, even if your quantum number is 0, you will always have this 1/2 h nu left over. And we'd like to get rid of this. And we can easily do this by redefining our new epsilon 0. This is supposed to be our vibrational harmonic oscillator 0 minus this offset. Okay. So we use this, and this thing we set to 0, right? So now we've shifted the origin of this entire harmonic oscillator to 0, and our 0 basically starts here, our new 0. Okay. So this means that our epsilon 1 now becomes h nu. Okay. And our epsilon 2 is 2h nu. Our epsilon 3 is 3h nu, right? You see, we still increase always by 1. Everything is just shifted by 1/2, okay? And so on and so forth. And now we go and and epsilon 0 is 0, of course, right? Now we insert this in our partition function, which, as always, is the sum over our states, right? We use the index n for vibration, just out of convention, minus beta e vip n, okay? Now, if we start using the eigenvalues I've listed before, you then get e to the minus 0, that would be 1, plus e to the minus beta h nu, plus e to the minus 2 beta h nu, and so on and so forth. And so you see that in general, what we have is a function that goes like this sum, right? I have some x, that would be e, and some exponent n, right? So this is a geometric series. And in particular, for 1 plus e to the minus x plus e to the minus 2x, etc., we know that this is 1 over 1 minus e to the minus beta h nu, right? So the n has been integrated out, if you wish, right? And this is a known closed form expression. Okay. Let's connect these. Okay, we've hit the hour. Are there any questions at this point? We did not manage to arrive at the final expression, but we'll do this next week. There's a question about the shift. So we did this shift precisely to obtain such a mathematical form here, right? Which then allows us to make use of this of the closed form expression for Q, right? And then later on, you will see next week we will reinsert this shift and correct it back again. So don't worry. Yeah. All right. I'd like to thank you for your attention, and I wish you a good weekend, and also a good reading week next week. And I'll see you not next week, but the week after in person in our usual wonderful lecture hall. Bye-bye.